Hello everyone. Welcome to the course on operating system. I'm Karthik Gopalan. In this lecture, we will learn about what is an operating system, what are its responsibilities, and what are the role of interfaces in a computer system design. So let's first begin by asking, what is an operating system? In its simplest form, you can think about operating system as a piece of software that resides somewhere in the computer's memory, just like any other piece of software. But there is a crucial difference between operating system as a software and any other normal user level programs that you run in your computer. Operating system happens to be the most privileged software in the computer. What that means is that it can do special things that other normal programs are not allowed to do. For instance, it can directly communicate with hardware such as disk or network, or it can control memory allocation. It can control which other process can access which parts of the physical memory. It can control which processes or which other software can run on the CPU for how long and when. So essentially, operating system can do special things that deal with allocation and control of a computer system's resources, which other normal software are not allowed to do. So broadly, these three resources, we can categorize them as CPU, memory, and I/O devices or input-output devices. So one might very reasonably ask why one needs an operating system in the first place. If we have a computer and its hardware resources available, then why can't we just run any program we want directly on the hardware and let it directly manage the hardware resources? So normally if you take a computer's hardware resources, the CPU, memory, and I/O devices, these are accessible to any software running on the computer through an interface, which is the hardware software interface. The hardware software interface has a specific name. It's called the instruction set architecture. Instruction set architecture, you can think of it as the set of instructions that a software can issue to the CPU, using which the CPU can then initiate actions to control various hardware resources. Now, any interaction between software and hardware happens through these ISA. And ISA is defined by the hardware vendor, such as, say, Intel or AMD. So if you essentially have a software that can directly run on the hardware, meaning it can issue instructions directly to the hardware, then why isn't that enough? Like, why do you need a special piece of software called OS to interject itself between your application and the hardware? So if you want, this is certainly possible. If your program was the only program running on the computer and it knew exactly what it was doing, how to communicate with the hardware, you could certainly do something like this. And many times when you don't want additional overhead, certain embedded systems, for example, might be designed to run a custom designed software for a specific hardware to do a very specific task. More often, regular user level programs don't know how to talk to the underlying hardware. There are various types of hardware with various peculiarities. There are various types of CPUs, various types of memory controllers, various types of disk controllers, and so forth. And it is almost impossible for any single program to know the details of how to interact with every single hardware device. So we might say that, all right, we can write some generic device driver software which can talk to these specific hardware devices and then provide them as, say, um, libraries of some sort to these programs. So any program that wants to run on a hardware, it could link in the necessary device drivers, and then once that's done, you could run the resulting binary directly on the hardware, right? So now we have begun to introduce aspects of modern operating system into into this picture between the user level program and the hardware, right? But if this was the only program to run on a given hardware, then it could link the necessary device drivers and happily have direct access to the hardware without any additional OS support. However, now let's consider a situation where we want to run more than one program on a given set of hardware. What that means is these two programs have to share the CPU, share the memory, and possibly share the I/O devices. So the question is, do we just rely on these programs to be nice to each other, or do we want some other additional piece of software to arbitrate between these two to have them executing nicely without interfering with each other? So uh, now we can add some additional software for multiplexing, for hardware multiplexing, or in other words, hardware sharing. What this means is that in addition to the device drivers that we saw in the previous slide, now we need some other software component to decide which of these two programs get to run on the hardware at any given time on the CPU, which parts of memory they can access, when they can access the hard disk or network card, and so forth. So now, as you can see, we are building scheduling and resource allocation into this intermediate software, which now looks more like traditional operating systems. Now, within this picture, assume for a moment that the two programs that are going to share this hardware, they don't trust each other, and they're mutually untrusting, or they can be potentially malicious. So we need some additional software that can enforce protection, meaning that it can protect one program from another program running on the same machine sharing the same hardware. So in addition to having device drivers for I/O and sharing or multiplexing mechanism for resource allocation, we need some protection mechanism to prevent illegal or unauthorized access to data and I/O devices by one program or the other program. So there are various types of protection models, or what are also known as more formally threat models, that one may have to consider. Of course, protecting one program from another is really important between, say, mutually untrusting users. But it's also important now that this intermediate software that's now our operating system, this itself becomes a target of attack because it has control over the hardware resources. So it's important to protect the operating system from other normal user level programs that are running on the system. So that's another aspect of protection. And then sometimes you have to protect the hardware from the programs. Some programs may not be allowed to, say, access certain hardware devices, say like the microphone or your camera. So who enforces these access control policies? Who protects the hardware itself? Well, again, that's the role of the operating system. And sometimes these programs may not trust the hardware. You might have malicious hardware on a computer that might affect the software program. So again, operating system plays a role here there where it might protect user level programs from untrusted hardware. So as you can see, protection can be interpreted in many different ways, and OS has a key role to play in all of these situations. All right, so now we know that OS has three primary roles, which is to manage I/O, to do multiplexing or sharing, and then to provide protection. But when does the OS do all these things? In other words, when does it run on the CPU? Under what situations does it run? So if you think about it, once an operating system boots up, then during the normal execution of your computer, there are a few events upon which operating systems code could execute. So I stress upon the word event because I'm saying, implying that the operating system doesn't run all the time. It normally runs in response to some events. So what can these events be? Well, the most common event is that, let's say you are running a normal user level program. The program needs some special service from the operating system, like accessing the file system or communicating over the network. In this case, the process would make something called a system call. It's like a request to the operating system. And when the system call is detected by the processor or the CPU, when the corresponding instruction is detected, then the CPU would switch control to a piece of code that handles that system call in the operating system. So, so a very common way to invoke the operating system code is through system call requests from user level processes to the OS. The other reason the operating system code could execute is due to exceptions. By exceptions, we mean that when a normal user level program, it does something that's usually wrong or incorrect. For example, a null pointer dereferencing, or divide by zero, or floating point exception, or segmentation fault, access to invalid memory locations. So, so these things are exceptions or errors that must be handled by the operating system. So in this case, the processor will again jump into operating system's code somewhere in memory, which will then handle the error and take appropriate actions, such as killing the process if there was a malicious action by the process. The other common reason why OS code would execute is because of hardware interrupts. So this is interesting that hardware can actually invoke OS code. And how can it do that? By sending interrupts to the CPU. So whenever hardware has some event to handle, for example, a network card receives a packet that has to be delivered to the OS and then to some process. So the network card would send a hardware interrupt to the CPU, which would then jump to some piece of OS code, which would handle that network interrupt, or a network interrupt handler. So for different types of hardware devices, you can have different interrupt handlers in the OS, and these interrupt handlers are sitting there in memory waiting for the event to occur, and whenever the event occurs, they get invoked, just like normal functions get invoked by a process, right? So all these three mechanisms we have discussed, they are in response to certain events. The OS doesn't run all the time, and when certain events occurs, system calls or exceptions or interrupts, the corresponding functions in the OS get invoked. Uh, and then there is a fourth mechanism which is more like traditional processes. Here, the OS, after booting up, it can start a bunch of persistent threads, or kernel threads. Uh, these execute regularly, periodically maybe, or maybe in response to certain events, but rest of the time they are in blocked state. For example, you might have some kernel thread to record all the events, all the critical events in the system, like system log daemons, and these might execute as kernel threads. Most of the time they are sleeping, and occasionally they get woken up and executed as kernel threads. So these are the four different ways in which OS code could get invoked, or run, as you may call it loosely: system calls, exceptions, interrupts, and as long-running kernel threads. So here's another view of the various layers of software that we have discussed so far. We have talked about processes that are normal user level programs. And then we talked about the operating system, which consists of various software components for performing I/O, for doing multiplexing, and for protection. And then processes can talk to the operating system through the system call interface. There is special requests to the operating system to execute certain privileged operations on behalf of processes. And then normally, an OS would directly interact with the underlying hardware through the instruction set architecture. But increasingly what we are seeing is another layer of software between the traditional operating systems and the hardware. And this software is called the hypervisor, which provides a functionality called virtualization. So what that usually means for most people is that you would be able to run multiple instances of different operating systems side by side on the same hardware. So hypervisor is like an operating system for operating systems. And most of the time, hypervisor tries to stay transparent, meaning invisible. Unlike operating system, which makes itself visible to processes through a system call interface. So processes know there's an OS and they can request certain operations to the OS through system calls. On the other hand, hypervisors normally try to make themselves invisible in the sense that the OS thinks it is running on bare metal hardware, but in reality, there may be a hypervisor that might be monitoring its actions, intercepting certain privileged instructions, emulating them, and so forth. In certain situations, the hypervisor, for performance reasons, the hypervisor may choose to make itself visible to the OS. And in order to do so, there might be a hypercall interface between the OS and the hypervisor. Just like there's a system call interface between process and OS, operating systems can use hypercalls to more efficiently request certain services from the hypervisor. So we'll talk more about virtualization later in the class, but also touch upon aspects of virtualization and hypervisor as we discuss other OS components. So in this slide, I want you to look a little deeper into the various interfaces available in the entire computer system, from the hardware all the way up to the software. So if you look at this picture shows um, the hardware software interface, which is right in the middle, labeled 7 and 8. As we discussed earlier, this hardware software interface is called the instruction set architecture, or ISA. Everything below that line is hardware, everything above that line is software. Now, uh, within the ISA, you can see that it is classified under two categories. The part labeled 7 is the user ISA, or user instruction set architecture, which refers to instructions that normal user level unprivileged programs can execute on the CPU without any intervention by the OS, without having to request permission from the OS. So these unprivileged instructions could be doing load and store to accessible parts of memory, or doing normal arithmetic operations or floating point operations, and so forth. And then the system ISA instructions are special instructions that provide privileged access to the underlying hardware. So because these provide privileged access to the hardware, only the operating system is allowed to execute this instruction. That's why it's called the system ISA. So normal user level programs would execute the user ISA instructions to execute on the CPU most of the time, and then when they need special uh, services from the OS, they would invoke system calls. The system call interface, as you can see, is labeled 3 in this picture, and the OS would then execute privileged instructions to service the corresponding system calls. So looking down at the hardware level, you can see there are various components in hardware, again connected to each other through hardware level interfaces. For example, the execution hardware, or the processor, and its registers forms the main interface between hardware and software. Below that, you would see that there are I/O devices at one end and main memory, or the DRAM, at the other end. So everything else in between is meant to have the CPU, I/O devices, and main memory interact with each other. So what that means is that the CPU might issue instructions to I/O devices to transfer data. So for that, there's a system interconnect bus which carries data between the CPU and I/O devices. But then the system interconnect bus may also enable the CPU to talk to the main memory through memory controllers and memory translation units. Um, and, and then the main memory and I/O devices may also directly talk to each other through the system interconnect bus. So as you can see from this picture, the system interconnect bus or the system bus plays a really important role in moving data and commands around between various hardware components. So the speed of the system interconnect bus is often really important for very high throughput, low latency data movement. Um, so normally system interconnect bus is more complex than what's shown in this picture. There are many system buses, some for high-speed devices and some for low-speed devices, and so on. Uh, so we are not going to go deeper into the hardware component, but it's important to keep this picture in mind as we discuss rest of the OS functionality. The one last thing I want to point out is that a combination of various interfaces have important roles to play in what the operating system does. So we've already discussed the ISA or the instruction set architecture. You can take a combination of the user ISA, which is number 7, and system calls, which is number 3, and if you look at this boundary formed by interface number 3 and interface number 7, this has a specific name called the ABI, or Application Binary Interface. What this means is that the ABI is the view of the rest of the computer system as seen by user level processes. Whatever user level processes do, they are either executing user ISA instructions directly on the processor, or they are executing system call instructions, which then transfer control to the OS to do something on their behalf. So ABI is really important for portability of programs, because if you take a binary executable and move it to a computer which has a different ABI, say a different user ISA or a different system call interface, then the program won't work, right? So ABI is really important for portability of binary executables. That's why if you say take an executable that's compiled for on Linux operating system and move it to say an identical hardware but which is running say a Windows operating system, then your same executable won't work, even though maybe the processor is still x86 processor. So what that means is the system call interface for Linux and Windows are different, so the ABI is different, so your executable is not portable anymore. The other interface that you might want to understand also is API, or Application Programmer Interface. This consists of another interface labeled number 2 for libraries. So when you, as a programmer, you write code, then you're using certain libraries which provide certain functions that are written ahead of time for you to use just to make your life easier. So these functions either get statically compiled into your program or they get dynamically linked into the program at runtime. And these are still user level pieces of code. So as far as programmer is concerned, the programmer needs to know this combination of interface, which is 2 and 7, which is what user level user ISA instructions to execute and what library routines to invoke. But once the program is compiled and are linked, then you don't actually deal with the interface number 2. So, so programmer has to know API, but during runtime, ABI is more important. So API is for programming time, and ABI is for runtime, right? So this brings us finally to a brief history of operating system, and it turns out the history of OS is really interesting, just like any other history of computing technology. So when computers started becoming mainstream around 1950s and 60s, these were mostly large mainframe computers. These were batch processing systems. You would feed in a job, the computer would just do that one job at a time. And then when it's done, it would pick up the next job. So users would provide their own operating systems as libraries that we discussed earlier to know how to interact with the hardware. And there was no multiplexing or protection issues in the earliest computers. As time went on, there was a need for multiple programs to be running simultaneously or concurrently. So multi-programming requirements led to addressing issues of hardware sharing, which meant that you had to bring in notions of concurrency, memory protection, formalize what it means to be an operating system, provide system call interfaces, and the hardware had to distinguish the privilege levels between the OS and user level program. So hardware provided this notion of a privilege level in ways for the OS to control privilege level transitions, and trap handling, meaning for exception handling or interrupt handling and so on. So one of the pioneering hardware in the early days was the Multics system, which had innovations in both the operating system and the hardware. With, that led to the development of the Unix operating system, which addressed many of the drawbacks of Multics. Multics itself was pioneering, but then Unix went further and introduced the notion of file system as a central organizing concept for all hardware and system resources. So Unix also introduced the C programming language, which is a fairly dominant programming language even today. And then in the 1980s, people wanted computers right on their desks, so that led to a personal computing era, and a lot of personal computers such as the Mac computer, the IBM PC, and uh, and of course the Windows and DOS operating systems came forth. Unfortunately, during this time, many of the lessons from the mainframe and multi-programming era were forgotten, and they had to be painfully relearned. In 1980s, also saw wider adoption of Unix, but also a fragmentation of Unix into uh, customized, commercialized versions from different companies, and this led to a lot of compatibility issues and fights over intellectual property and copyright. And at the same time, open source movement was taking root, and from that came operating systems such as FreeBSD and Linux, and these kind of led the way in democratizing and commoditizing operating systems. Uh, so, so this also coincided with the rise of the internet, uh, and and together they have led to the computing landscape that we see. So in the 1990s, it was also very interesting in that from the notion of processes, the use of threads became more prominent, more mainstream, because now there were CPUs and being designed that had there were multiple CPUs to be handled, and there were multi-core CPUs that were coming out, and parallelism was becoming really important, and operating systems had to be redesigned to handle parallelism and concurrency and higher performance requirements. So in 2000 and later, the last 20 years, essentially, cloud computing became very prominent as internet matured, and large data centers came up. At the same time, mobile devices such as handhelds became very important, and all these platforms required operating systems. So the traditional open source operating systems such as Linux are uh, being adopted to run on these various platforms. So, for example, Android is a variant of Linux. iOS is again like a variant of Unix that descended from Apple's own version of operating systems. Um, at the same time, we talked about hypervisors earlier, so operating system for operating systems. So these have also risen. They were not necessarily new. Mainframes already had the support for hypervisors, but again, these were forgotten, and they had the concept then was born again with the rise of cloud computing. So companies such as VMware and Zen pioneered virtualization, and now even commodity operating systems like Linux have support for hypervisors. So this brings us to the conclusion of the history of the OS. Of course, things are evolving even as we speak, and various kinds of new abstractions and new designs for operating systems are being explored even today. So There's going to be a really exciting time in the future, especially with Internet of Things, and 5G and artificial intelligence, how these influence the design of operating systems going into the future.